This section of lecture will cover nucleophilic addition reactions to aldehydes and ketones that involves carbon and nitrogen nucleophiles, and we'll have some kind of following reactions on a couple of those. So I'm going to start with Grignards as a carbon nucleophile. We studied Grignard reagents in Chapter 17, and actually they were introduced back in Chapter 10. We use them in Chapter 17 to make larger alcohols. And these larger alcohols took advantage of the fact that we have a lot of negative character on the carbon from the Grignard reagent, and then it will react with the carbonyl carbon. Now, in the book, they show this complex first with the magnesium, and I tell you that this carbon has a lot of negative character, and so it's going to work. We don't need acid catalysis. Basically, we have this works without any acid being present, and you get to your tetrahedral intermediate, and it stays like this until you add water or aqueous acid in the workup, and then it picks up a proton and the magnesium stuff goes into the aqueous solution. And so this counts as a reduction because the carbon is bringing a pair of electrons, and so this carbonyl carbon gets reduced to an alcohol level carbon. And this time, if we think about the degree of the carbon, an aldehyde, this would be a primary carbon. We've added another carbon, so it's going to go to a secondary carbon alcohol. If you had a ketone, it would have been a secondary carbon. It's going to end up as a tertiary alcohol. So here are some examples. So if I have this ketone, again, this carbon right here is the nucleophilic carbon, the one that's directly attached to magnesium. So we're going to attach that carbon to this carbon, and that's going to push the electrons on out to the oxygen, which is going to pick up a proton when we put in the aqueous acid. So whatever comes along with this carbon, you just bring it along, and so that's out there. Here's another example. So this carbon right here that's directly attached to magnesium, that's the one with negative character. So that carbon gets attached to this carbon, and all the carbons stay there until you put in the aqueous acid. You pick up a proton on the oxygen. So we've seen that before. So now let's talk about cyanide ion. So if you look at the formal charge argument about cyanide ions, you can figure out that the carbon is the species in here that owns the negative charge. And so that's going to be the more nucleophilic end of this ion. And we can get the cyanide ion from hydrogen cyanide gas dissolved in water. Probably people don't like to do that very much because of hydrogen cyanide gas being pretty scary to work with because of the toxicity of it. But we can also use a cyanide salt like potassium or sodium cyanide in an aqueous acidic solution, and that will provide us with some protons for the protonation end of this, and also with cyanide ions. If you just think of HCN by itself, it's a weak acid, and so there's not a lot of cyanide ions available. But technically, what we're doing is we're adding HCN across the carbonyl double bond. So all of this molecule gets incorporated in there, but we don't necessarily have to actually do it from here. And this reaction can be reversible, so let's look at some examples. If you put in HCN, you put the hydrogen up here and the cyanide ion down here, and so you make this kind of a product, and this is called a cyanohydrin. You may remember we used the term hydrin when we talked about halohydrins in the alkene chapter, where we added HBr, bromine or chlorine molecules in aqueous solution. So we added the OH to one of the carbons of the alkene, and a halogen to the other carbon of the alkene, and we had to figure out, that the halogen went on first, so it went to the less substituted carbon and all that. But anyway, the halohydrin, that terminology, hydrin means there's an alcohol and something else is either on the same carbon, or in this case, or an adjacent carbon, as in the case of halohydrins. So that's where you've seen that term before. And cyano is the common name for the CN group. And so one of the things that's happened now is not only have we made a new carbon-carbon bond, but we've also brought a nitrogen into the molecule. And so that molecule is now one carbon larger than the starting aldehyde or ketone, and it's got this nitrogen in there. If we use an aldehyde, we can make a cyanohydrin out of that too. And so that's one way to write this. Like I said, we may also write it with a salt like KCN and aqueous acid would accomplish the same thing. So why are we interested in that? Okay, so here's a simple example of making acetaldehyde into a cyanohydrin. If we react this with aqueous acid and heat it up, we can actually hydrolyze this to a carboxylic acid. Now, I've told you that carboxylic acid carbonyls are at a different redox level than aldehyde carbonyls, and this molecule is also one carbon larger. And it turns out, this is just simple hydrolysis, that this carbon and the cyanide carbon are in the same redox level. Nitriles are actually a derivative of a carboxylic acid in that sense. And we'll talk more about that in chapter 20 and 21. But this particular type of molecule is called an alpha hydroxy, because there's an OH, an alpha hydroxy acid. Well, you may have heard of alpha hydroxy acids before. This particular example is lactic acid. Alpha hydroxy acids are used in some facial cleansers and things like that for because they're all natural, and of course they don't necessarily have to be all natural. They can be made industrially with simple reactions like this. The other reason we're interested in this is because, once again, we've incorporated the nitrogen, as the cyano group contains the nitrogen. So here's an example of a cyanohydrin from cyclopentanone. And if we do a reduction of this nitrile, we can make an amine. And so this is the first time that we've made an amine other than on aromatics. And we're not going to emphasize these two subsequent pathways in this chapter so much, but just in case you're wondering why is it so interesting to make a cyanohydrin, or why do people care, well, these reasons are really important, that we can go on to alpha hydroxy acids, or we can go on to primary amines. Those things are important, and why we care about being able to make cyanohydrins. And incidentally, this is an inorganic, quote-unquote, inorganic source of carbon that we have now incorporated into our organic compounds. Okay, another carbon nucleophile is called a Wittig reagent, and this is German, so it's pronounced, the W is pronounced like a V. And before we can actually see the reaction itself, we need a little background on what is a Wittig reagent. And we're going to be doing some SN2 reactions, so you may have to think about what does that mean. SN2, remember, was nucleophilic substitution, that's second order kinetics, and so that means that the substrate can't be too crowded. And so we're going to use an alkyl halide substrate for an SN2 reaction with a phosphorus nucleophile. And nucleophilicity improves as you go down the periodic table. So phosphorus is a better nucleophile than nitrogen, but it's also larger, and it can take more oxidation states. So when we talk about an SN2 reaction, the nucleophilic crowding is important, and so that's why we really work this with really not crowded substrates with the phosphorus nucleophile. And and then what's going to happen after we get through that stage of things, then we're going to see that the phosphorus and the oxygen actually carry on a subsequent reaction. And there are a lot of examples of biological situations where phosphorus and oxygen are involved. So you can kind of appreciate that perhaps. And we're going to see some examples of a simple phosphorus compound and one example of a base that we're going to need as we go through this process. But I can tell you there are actually lots of phosphorus compounds that can work and other bases that can work. It just depends on the particular molecules. So it's been simplified basically to the original Wittig reaction, how it was structured when they first discovered it, or Dr. Wittig first discovered it, but it is pretty general, and we'll also talk about why we're interested in this when we look at the examples. So first let's consider the preparation of the Wittig reagent. I've told you a little bit in the past a few times that if you look at this, this is benzene. But if we want to use it as a group, you know, you take one of these hydrogens off and you attach it to something else, then that's a C6H5 group, which is sometimes also abbreviated PH, which is short for phenyl, as a group name, and actually chemists like to abbreviate it as a capital Phe. So you might see this compound where you've got 3 of these benzene rings attached to one phosphorus. You might see it written this way, where you have 3 of these phenyl groups attached to one phosphorus, or it might say 3 pH3 attached to a phosphorus, or Phe3 attached to a phosphorus. All those things are just shorter and shorter ways to abbreviate all this big gigantic drawing. And the phosphorus has an unshared pair of electrons on it. And remember that this guy is actually something like sp3 hybridized, so it's not really flat like that. And so here it is in shorthand. This guy's pair of electrons can act as a nucleophile and do an SN2 step where it reacts with this carbon and spits out this halogen. And so in your SN2 step, when you put a 4th bond on the phosphorus, just like nitrogen, it gets a plus charge. And so this guy is called a phosphonium salt, and the anion to go with it is the halogen that you just kicked out here. And by the way, this stuff is white, and most of these are colorless, and these salts are white or pale yellow. And then we're going to use N-butyllithium as our base. Now, N-butyllithium is just normal straight chain 4-carbon series attached to a lithium at the end. And the carbon-lithium bond is very, very polar because of the big difference in electronegativities between carbon and lithium. And so these guys are often used as a base. And we've talked about making organolithium compounds before. You start with an alkyl halide, you put in lithium, and there you go. But the carbon has a lot of negative character, so it's a really strong base. And also the reason this is popular as a base is because the other product, when this guy picks up a proton, is just butane, which is a gas, and so it can just go away. So this guy is going to be able to pick off a hydrogen as a proton from this molecule. You know, we've talked about the kind of the tug-of-war argument when you have electronegativity differences or polar bond differences, that it's felt nearby. So this real honest-to-goodness plus charge on this phosphorus is pulling electron density toward itself, and so it makes these next-door CH bonds also very polar, and so these hydrogens are acidic enough, this really strong base can pick it off. Now, I said earlier on that we can have other phosphorus compounds, we can have other bases, and so these are the places where we could have, you know, differences. We don't have to use this particular phosphorus compound, we don't have to use this particular base, but those are the ones we're using in the examples in this book. But in lab, you may use something else. We sometimes do Wittigs in lab. When you get to this guy, now you've picked off this guy as a proton, that's going to leave a negative charge here. This guy has a plus and a minus right next to each other. Well, it turns out that phosphorus can take 5 bonds. Nitrogen's too little, it can't do that. But phosphorus can actually take a 5th bond, and so you actually have a kind of a an equilibrium here, or resonance, if you will, where the phosphorus and the carbon actually have a double bond between them. And this guy's called an ylide. And this guy is usually colorful. So we went from white and colorless and pale yellow, colorless, to probably bright red, kind of a blood red. And again, whether it's got a lot of color to it or not depends on the particular phosphorus compound, the particular base that, well, not so much depending on the base, but the particular phosphorus compound and what your R group is here. And by the way, not only did we need this to not be crowded so that we could do an SN2 reaction on it, but we also have to have at least one hydrogen here, or else we couldn't go through this step. And so this guy is called the Wittig reagent. So we've done all this to get to this species. Whether you see it drawn this way or this way, this is the Wittig reagent. And this guy is also called an ylide, because of this charge separation and this little bit of resonance that it can do. And it will act as a carbon nucleophile, because when it's in this form, you can see the carbon that has a negative character, negative charge. That's the nucleophilic atom. So they've drawn it like this, and now they're using the pH3 as the abbreviation for the phenyl group. And so your carbon has negative charge, reacts with the carbonyl carbon, and now you get this tetrahedral intermediate, and you notice that they've drawn it in such a way that the phosphorus and the oxygen are sitting right next to each other with opposite charges, and so you get an electrostatic attraction there, and you're going to see a bond form between the oxygen and the phosphorus. And then, all of a sudden, the oxygen and the phosphorus say, let's just leave. And you get a little pericyclic step here in this spontaneous decomposition they're talking about. And so this pair of electrons goes with the oxygen and the phosphorus, and this pair of electrons stays here, and you end up making a new double bond. And so, if we go back, we started with the carbonyl carbon, with this double bond to oxygen. We end up with the carbonyl carbon double bonded to a different carbon. Okay, so you've made a bigger molecule, so you've put together a chunk of carbon from here and a chunk of carbon from here. You make a new alkene that's bigger, and one of the things that you might notice is we know exactly where the double bond is going to be. It's going to be between the carbon that was originally the alkyl halide carbon and the carbonyl that was originally an aldehyde or ketone carbon, are the two sources of carbons. We know that that's where the double bond is going to be. We don't necessarily know about cis and trans isomers, but at least we know exactly where the double bond is going to be. When you start thinking about, okay, why are we interested in this, and you go back and you think about ways that we've had to make alkenes, some of those reactions led to mixtures of where is the double bond going to be. When we did elimination reactions, we didn't have that problem when we did alkyne reduction, but when we did elimination reactions, dehydration or dehydrohalogenation, we could sometimes get mixtures of where exactly is the double bond going to be. So this is interesting from that standpoint. Also, when we did those kind of reactions, we weren't changing the number of carbons in any reducing alkynes or doing elimination reactions to make alkenes. All of those did not change the number of carbons. So there's several reasons why this reaction is interesting. So let's look at some examples and look at it drawn in several different ways also. So here we have an alkyl halide. We can create a Wittig reagent with that if we react it with the triphenylphosphine and N-butyllithium. Now here's a picture of the ylide. Now I've kind of turned it around, okay, but it doesn't really matter. This carbon that was originally attached to the chlorine is now the carbon that's attached to the phosphorus. And after treatment with the base, that's your carbon nucleophile. And it's going to react with this carbon right here. And when all is said and done, we will have a double bond between this carbon, which is this carbon, and the carbon that was originally attached to halogen. We now have a double bond between those two guys. And we've added together all these carbons and all these carbons to make a new molecule. Another way you might see it written is without the detail of showing how you prepared the Wittig reagent. So here the Wittig reagent's already been made, and so we've got it drawn like this, where there's the carbon with a negative character, and it's going to react with this carbon. Again, we're going to make a new double bond between this carbon and the carbon that was the carbonyl, and there's your product. Okay, so if you were doing a synthesis problem where you had to show the sources of everything, you would have to show like this, where did this come from? You'd have to show where did this come from. And of course, if we were starting with alcohols, which we typically do in synthesis problems, you'd have to make this from an alcohol, you'd have to make this from benzene. So, so here again, just sort of summarizing. We know exactly where the double bond is going to be, and we're going to make bigger alkenes from two smaller pieces. Okay, so let's shift now to amines as nucleophiles. When we talk about amines, first we need to understand what we mean when we talk about the degrees of amines. And it's a little different than when we talk about the degrees of carbons. We talked about the degrees of hydrogens and alcohols based on the degree of the carbon that they're attached to. In the case of amines, we're going to talk about the degree of hydrogen, the degree of the nitrogen based on how many hydrogens are missing from the parent molecule, which is ammonia. So ammonia is our starting point. If we take one of those hydrogens off, then we're going to call that a primary amine. And it doesn't matter what you put in place of it. So you could put OH on there, you could put carbon on there. The degree of the carbon doesn't matter. All of these things are something in H2, and these are all primary nitrogen. So these are all examples of primary amines. And if we take two of the hydrogens off of ammonia, again, it doesn't matter what we put in place of them. If we've got only one hydrogen on the nitrogen, two of them are gone from ammonia. These are all examples of secondary amines. So I have various degrees of carbon, it doesn't matter. It's just how many hydrogens are missing from ammonia. So we're down to one hydrogen, these are secondary amines. If we take all three hydrogens off, then it's a tertiary amine. And they could all be the same thing. You can have aromatics. You know, there's no hydrogen on either of these two nitrogens. These are both examples of tertiary amines. If you put a fourth bond on this nitrogen, then those are called ammonium salts, and then it doesn't really matter about the hydrogens. It's just if it's got four bonds, it's called a quaternary ammonium salt. And we're interested in this chapter about talking about amines as nucleophiles. The guys that are primary and secondary amines are good nucleophiles because subsequently they can lose a proton, a hydrogen as a proton, and go back to a neutral state. Tertiary amines can't, they don't have anything to lose that's easy like that, so they don't make good nucleophiles. And of course, quaternary ammonium salts don't have a free unshared pair of electrons, so those aren't good nucleophiles either. So we're going to talk first about primary amines as nucleophiles, and then we'll talk about secondary amines. There are some differences in how they come out when we talk about their behavior with aldehydes and ketones. So, firstly, we'll talk about nitronucleophiles that are primary amines. And you know, we were talking about whether or not we need acid catalysis, and it turns out that these things are very pH dependent as to how well they proceed. Now, they didn't draw that in this book, in this thing in the book, but I will show you in a second that they're very pH dependent. So we actually are going to start out by protonating most of the time, but the nitrogen is the nucleophile on the carbonyl carbon, and you get a proton off of here, and you get a proton up here, and so you make a product that looks like a hemiacetal. And this guy, this called a carbanolamine, isn't really stable. So the hemiacetal, like in the sugar molecules, you could actually stop there, or they do stop there. These carbanolamines can be isolated, but they're not very stable, and so they tend to do something else, which would be kind of like what we talked about, the acetal, sometimes they don't stop. So in the book they have this little graph of the reaction rate, and so we're talking about nucleophilic addition reactions with amines as a function of pH, and you'll see that the reaction works best at about a pH of 4.5. And the reason is because if you have too much acid, then the amine would be protonated. Amines are bases, and so if you put them in strong acid, they get protonated. And if the pH is too high, then what we're going to look at next can't happen because you don't have enough protons. So here we go. From the carbonylamine, we put the proton back on, and just like in the acetal case, it could go on to the oxygen and make a water molecule. And the nitrogen can facilitate the loss of that, just like oxygen did in the case of acetal formation. And you lose this water molecule, and then you can lose this proton, and you can get to this situation, which is called an imine. Now, what happened in acetal formation is from here, this guy would have reacted with the carbon. But because the nitrogen has a proton to lose, we can just go to the imine. And imine is analogous. It's the same redox level carbon as an aldehyde or a ketone. That's the same redox level. And so you haven't actually changed the redox level of the carbon when you've done this. And this is one of those things that I said would we would go on past the nucleophilic addition reaction, and sometimes we would end up with a double bond. You notice we did that with the Wittig. We ended up with a double bond between the carbon and whoever the nucleophile was in the Wittig reaction. All of the nitrogen amine type reactions are going to end up with a double bond between the carbon, and that was originally the carbonyl carbon, and another atom, and in this case it's the nitrogen. So we again only need a catalytic amount of acid, and so this pH dependence is because we have enough acid to make this work, but not too much, because that would interfere with the first part of it, and too little would make it hard for this step to occur. We'll see more about amines later in the book. They're going to be important later in the book, in the amines chapter. The real story here is that what you're doing is a dehydration, and you're taking the hydrogens from the nitrogen and the oxygen from the carbonyl compound, and you're making a water molecule, and you left with everything else that was attached to nitrogen, and it's double bonded where the carbonyl used to be. So this is what I call the duh thing. Okay? And in case you're wondering, this is also an important biological process, and the products, we call them, chemists call them amines. Biologists usually call them Schiff's bases. In any event, that kind of thing is pretty easy to do. It doesn't matter, you know, as I said earlier, as long as there's 2 hydrogens on the nitrogen, whatever else is on there, you can get this to work. But I am going to show you a few specific examples, because often they have been used as a way to identify ketones and aldehydes. So let's look at a few more examples. And these are pretty classic. This molecule right here is called semicarbazide, and you might think of it as a derivative of urea. Remember, urea just had nitrogen on either side of the carbon, and that would be an NH2 here. So you have 3 nitrogens, and so if you're trying to figure out who's going to be the nucleophile, well, it can't be this guy in this case, because we're looking for an NH2. And it's not going to be this one, because being right next to the carbonyl means that this pair of electrons is interacting a lot with the carbonyl. Remember, if you have a pair of electrons one atom away from a pi system, you can draw a resonance structure for it. And so this pair of electrons is a little bit tied up. And so this turns out to be the best nucleophile of all of these nitrogens. And so we take that guy, make a new bond between that carbon and that nitrogen, and here you go, we end up with a double bond there, and this kind of product is called a semicarbazone. These guys are white solids, and so if you had a ketone, you can make it into a semicarbazone derivative and take a melting point, and that would help you identify your original ketone. Another example, this is called hydroxylamine, and so that's an example of a primary amine. And so again, you do the same thing. You get your double bond between the carbonyl carbon and this nitrogen, and you lose these two guys and this guy is your water molecule, and you make oximes are what these are called. And again, these are solids that you can characterize to help you identify the original starting material. Now, we're going to go on in a minute and talk about hydrazine, which you may have studied a little bit in general chemistry. Sometimes I use it as an example of some examples in redox chemistry and in general chemistry. Hydrazine can be and is used as a propellant in rocket fuel because it can self-redox. But we can also use it as a reducing agent. It's going to give up hydrogens with electrons, and we're going to turn the nitrogens into nitrogen gas. And so there's the potential for a fairly innocuous side product of nitrogen gas to come out of here. But the hydrazine itself is a gas, but we can keep it in solution or as a salt, and it's a little easier to deal with. So we're going to talk about hydrazine a little bit later in this chapter, but before we talk about hydrazine itself, I want to talk about a couple of derivatives of hydrazine. So if we take one of those hydrogens off of hydrazine and put a benzene ring, a phenyl group on there, this is called phenylhydrazine. And again, we're just using this as an example of a primary amine. This is going to be the more nucleophilic atom in this in between these two nitrogens. So we'll just make a double bond between that nitrogen and this carbonyl, and there you go. There's a product, and this is called a phenylhydrazone derivative. And these guys, you know, all this stuff is still white or colorless, but again, these have been used as derivatives. If you instead put a couple nitros on here, you remember nitro, how that looks when you draw it out. There's a double bond to one of these oxygens, and you've got extended conjugation in here. This stuff is kind of an orangey red color. And so if you do the reaction with your aldehyde or your ketone, you've got this orangey red solution and this colorless solution. You mix them together and you get an orangey red or a yellowish orange precipitate. And these guys are called, this is 2,4-dinitrophenylhydrazine. The products are called 2,4-dinitrophenylhydrazones or 2,4-D or 2,4-DNP derivatives. And we use this reaction to test for the presence of an aldehyde or ketone. So you've got everything in solution, you get a precipitate, and that's a positive test. Visual, the formation of that precipitate tells you that you have an aldehyde or a ketone. And so that's kind of a classic test. So, back to hydrazine itself. We can do something else beyond the reduction, beyond the nucleophilic addition reaction if we have an aldehyde or a ketone. Now I want to re-emphasize that aldehyde and ketone carbonyls are different from the carbonyls in carboxylic acids and the derivatives. I can't say that often enough. You really need to keep straight that these are different. Okay? We're going to use the hydrazine itself, and it's going to go to the amine just like the derivatives did. And so here I've got that in brackets. Okay, so you start out with the hydrazine. You actually don't need to worry about the pH because this stuff is pretty reactive. And so one of these nitrogens, and it doesn't matter which one, is going to make the double bond with the carbon. And you get to this amine type derivative just like you would expect. And then, because of the presence of this base, it's going to start picking off these hydrogens and ultimately lose this right here, the electrons are going to flow into here and back down to here. This guy's going to pick up the hydrogens from the solution, and you will make an alkane type carbon out of what was originally a carbonyl. So you've done 2 levels of reduction, because when you get to here you have no reduction. That was just an addition and then elimination, and so you haven't changed the redox level yet. But once this carbon that was here starts getting these hydrogens, then you're accomplishing reduction. So remember that this guy's in the middle of the redox family, and it's gone down to an alkane type form, and so it's gone through 2 levels of reduction. So here's a little more detail. So when we get to that imine, I told you the base is going to start picking off the hydrogens, and when it gets to here, this anion can flow the electrons down to this carbon, and when it gets down to here, then it says, oh, I'm a carbon anion, that's pretty basic, picks up a proton from the solution, and now another base can react with this proton. Now that's where you get the second pair of electrons between these 2 guys. All that needs is to lose this pair, and there's your nitrogen molecule that forms. And again, this carbon anion will rapidly pick up a proton from the solution. So both of these 2 hydrogens come from the aqueous solution in this reduction, but the electrons actually were given up by the hydrazine hydrogens. Alright, so I said the nitrogen nucleophiles that are secondary amines, we would look at those separately, and the products are going to be a little bit different, and we'll see why when we look at some pictures. But the products are going to be called enamines, and this name comes from a combination of alkene and amine on the same carbon. And so we're going to see these as important intermediates to other compounds. They were never used as classic derivatives the way that those examples that I talked about were, but they are very useful. We don't do a lot with those in this book, but they really are important compounds, and also, of course, they have a lot of biological significance as well. The other thing that's a factor is our aldehyde and our ketone that we're going to use must have at least 1 alpha hydrogen in order to do this reaction. And because we're going to make an alkene that could technically be on either side in a ketone, you could have mixtures. So the examples in the book, if it's a ketone, it's going to be a symmetrical ketone, so I can't tell the difference as to which side is which. And the aldehydes, of course, only have 1 alpha position, and so it doesn't matter on that. And again, if you kind of take the duh approach, you're losing the oxygen from the carbonyl, 1 of the alpha hydrogens, and like I said, you have to have at least 1, so an alpha hydrogen, and the hydrogen off of the secondary amine. You're losing all of that to make a water molecule, and we're making a bond between the nitrogen and the carbon. And the reason you have to have the alpha hydrogen is we're gonna make a double bond to that. So again, we're not changing the redox level of the carbon. It's sp2. It's still sp2. When we take and make the bond between this nitrogen and this carbon, that would put an extra bond on that nitrogen, and the way to get the extra electrons to flow and release that, we lose that hydrogen, but we needed another bond to this carbon, and so that's where this hydrogen comes out. So let's say that we had this molecule. Our first job is to recognize that it's an enamine. So you look at this molecule and ask yourself, what functional groups are present here? Where there's an amine and there's an alkene, and they are both attached to the same carbon. At that point you should go, oh, that's an enamine. As soon as you think, you'll recognize that this could have come from a carbonyl compound. And where was it? The carbon that's attached to both the amine and is part of the alkene, that carbon right there was the carbonyl carbon. And because it still has a hydrogen on it, it would have been an aldehyde. And so this is the bond that we could have just made in the reaction. And so there's our 3-carbon aldehyde, and the rest of this stuff was all the amine, and it was a secondary amine, and the pH again is helpful to control the pH in these guys. And that is the end of my discussion of nucleophilic additions involving carbon and nitrogen nucleophiles. What remains in this chapter is the alpha beta unsaturated aldehyde and ketone reactions.